one-to-one functions. Now I'm going to tell you the truth about something. It took me absolutely forever to understand what a one-to-one function was. And when I finally, and I did not understand what a one-to-one function was until I started teaching. And finally, when I realized exactly what it was, I was like, why were you so stupid? Why? That was not hard. And I have no idea why it would not sink into my brain. So please don't make it harder than it is, because it's really not at all. We're going to look numerically, graphically, and analytically. So tables, graphs, and algebra. What's a function? So you're reading it off the filled-in notes, and that's totally fine. Remember that on a function, every x value has exactly one y value. Every x value in the domain has exactly one y value. No more, no less, one. So let's look at that next question. Now don't cheat, okay? Don't just look at don't cheat. If the point 2, -3 is on the graph of a function f of x, then no other point can have a let's draw it. Let's draw it. I don't want that. The point 2, -3. 2, -3. No other point on that curve can have what? A what of 2? Can have an x value of 2. Right. No other point can have an x value of 2. Could another point have a y value of 3? Oh, wait, of -3, my bad. Could we have that? Is that still a function? Yeah. That's still a function? Heck yeah. Heck yeah. Those are all fine. What's not fine? That's not fine. So you cannot have another point that has an x value of 2. However, it is possible for another point on the graph to have a y-coordinate of 3, just like we just showed. Now, so if a function means every x value in the domain has exactly one y value, a one-to-one function is a function where every y value has exactly one x value. So it's backwards. Every y value has one x value. So a one-to-one function is like this. Every x matches with one y, and every y matches with one x. It took me forever to understand that, and I still don't know why it took me so long. Every x has one y, every y has one x, period. So let's see what this says. For example, if the point 2, -3, and 5, -3 are both on the graph of f of x, it helps me to, I don't know. Huh? It won't let me do what?
It never lets you change when you scroll down.
If I plot 2, -3, if I plot 2, -3, and 5, -3, if those are both on the graph, namely, dummy, there is a y value, namely -3, this negative should be down here, that has more than one x value. Do you see that you have a y value that has more than one x value? That function is not one-to-one. Now, there's a little test. You know how the vertical line test tells us whether we have a function or not? A horizontal line test tells you whether we have a one-to-one function or not. We can abbreviate that HLT. So we can say a horizontal line test will determine if we have a one-to-one function. So remember, a function passes the vertical line test. a one-to-one function passes not only a vertical line test, but also a horizontal line test. So let's talk about numerical, graphical, and analytical. This is where you're going to just look in the filled-in notes, please. There's a term you probably have not heard that's in that first box, and it's discrete. You ever heard discrete involved with math? Yeah? No. Okay. Choir selling cheesecakes. I know because I've been asked like 6 times. The number of cheesecakes. Total, what do I want to call it? Your total, the amount of money that you've made. Let's revenue. Because revenue, remember, revenue means I haven't taken out my cost yet. Say that each of these represents 1. And how much are your cheesecakes? $21? Okay. That's better than Cheesecake Factory, I suppose, huh? I love Cheesecake Factory, but their cheesecakes are really expensive. Let's just pretend we're going that way, okay? So 1 cheesecake, $20. 2 cheesecakes, your total revenue, you're $40 and like that, right? Does it make sense to connect the points? Why? Because you cannot sell 1 1/2 cheesecakes. You cannot sell 2 2/3 cheesecakes. This is an example of a discrete function because it makes no sense to connect the points. So look at your box. If the function is discrete, meaning the points are not connected, the function is 1-to-1 if there are no repeating y values. No repeating y values. If the function is continuous, meaning the points are connected, the function is 1-to-1 if the y values are always increasing or always decreasing. Let me show you what we're talking about in that regard. Let's make a continuous function. Is that function 1-to-1? No, because if you make a horizontal line through it, it's going to fail. Is this function always increasing? Is it always decreasing? What's it doing? Both. It does both. If my function was only increasing, would that pass the horizontal line test? You betcha. If my function was only decreasing, would that pass a horizontal line test? You bet. So if the function's continuous, the only way it's going to be 1-to-1 is if it's always decreasing or always increasing.
So why is it being discrete? What does discrete have to do with it?
Because if it was discrete, this is not a good example, cheesecakes and profit. It's not a good example. But let's just say I had this. If I connected those points, then that would fail a horizontal line test. But every one of those y values, since they're not connected, every one of those y values is different. Does that help? So on the graphical, the function's 1-to-1 if the graph passes a horizontal line test, and you can abbreviate that HLT. The analytical one's kind of stupid in my my thoughts. Analytically, recognize the shape of the graph if we know the equation and whether or not the shape of the graph passes the horizontal line test. I think all that means is like if I said f of x equals x squared and you'd say, well, I know what x squared looks like, it looks like that, and no, that doesn't pass a horizontal line test. Did I say that too fast? If I tell you, visualize the graph of f of x equals x squared, you could have a picture in your head, couldn't you, of x squared, right? Does that pass a horizontal line test? No. So to me, that's just a visual. Can you picture it in your brain? And if you can, would that pass a horizontal line test? Now, do not look at your filled in notes right now. We're going to do a brain dump. You ever heard of a brain dump? What I want you to do with somebody near you is I want you to say out loud everything you know about inverses. From before this class, anything we might have talked about in this class was just a little bit. Anything. What do you know about inverses? Go. Let's talk about some things that you remembered about inverses. Here's what I heard. You switch the x and the y. My question is, why do you do that? So how does that do it? What else do you remember about besides switching x and y? Do you remember anything else? Okay, so you're kind of along the lines of Sarah. You want to use the word opposite, but as she said, that's kind of loosely used. Say again? Good. Reflex over the line y equals x. They undo each other. Inverses undo each other. What undoes x plus 6? What undoes adding 6? Subtracting 6. What undoes multiplying by 3? Dividing by 3. What undoes a square root? The square. The square. Okay. Look on your filled in notes. The inverse function is defined to be the function formed by switching the domain and range values of a function. That's the switching the x and y part. Now the question is, why does that work? I want to show you something. Okay, I wasn't trying to change a color, I was just trying to go down. Isaiah said that a function and its inverse reflect over the line y equals x. Do you remember, and this is from yesterday's notes, the first set of yesterday's notes, if a curve or a graph has symmetry with respect to the line y equals x, then what we learned was if xy is on the curve, then what other point is also on it? Ladies and gentlemen, that's why you switch the domain and the range. That's why you switch the x and the y. Y goes in place of x goes in place of y. Because if you reflect a point over the line y equals x, then the x's and y's change. So the domain of a function, think about this, is the what of its inverse? The range. The domain of a function is the range of its inverse. The range of a function is the domain of its inverse. Now I'm going to give you a problem. I don't want you to write anything down necessarily, but this is not in your notes. I was thinking about this last night. I give you this. Without doing the algebra, can you come up with a way to undo this and just end up with the x? Now keep in mind, this says y equals 3x plus 2. Using order of operations, what happened first? What would you deal with first? The multiply. You multiply by 3. And then add 2. If you want to undo it, you have to go backwards. Now go backwards. So if I was going backwards, I would have to subtract 2 and divide by 3, right? So here's what we're thinking. We're thinking maybe this one undoes this one, right? Let's come up with some points. What if x is 4? What's y? 14. Over here, what if x is 14? 14 minus 2, 12 divided by 3. Look at that. The x's and y's change. What if x is negative 1? Oh, no, I don't want to use that because I get negative 1, don't I? Yeah, I don't want to use that. What if x is negative 2? Negative 4. Over here, what if x is negative 4? Negative 4 minus 2, negative 6 divided by 3. Oh my goodness. Look, if xy was on that function, then yx is on its inverse. If xy is on a function, then yx is on its inverse. A function and its inverse undo each other. We didn't use any high-level mathematics to think through that. Now, do I want to do it with that one? No. Oh, sorry. Just going up here. We need to look at that very last question there. What property of a function must exist in order for inverses to exist? You may have had teachers lie to you a little bit in the past. What's the inverse of x squared? Now, are you thinking like this? Is the inverse of a parabola that opens up a parabola that opens on its side? Why is it just half? Huh? 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 Really? This is y equals x squared. Let's come up with some points on that curve. If x is 2, I'm not using 0. I'm not using anything where the x and y values are the same. If x is 2, 3, negative 2, negative 3. What undoes the square? So the inverse ought to be this. All right. What if I let x equal 4? I want you to look right here. The only time you are going to use plus or minus is when you actually put the square root in. You actually do this. I have to take the square root of that. If it's already there, then you only do the sign that it tells you to do. What's circled? There's a positive right there. This only says I want the positive value of x, of the square root. So the answer to this is only this. The answer to this is only 3. Now, so what happens is, are you in your room? Yeah. Miss Tennant, SOS, just, if I graph this, and I know that's crooked. I'm only going to get this part. Here's the deal. Is this function, y equals x squared, 1-to-1? No. This function then does not have an inverse that is also a function. You cannot have an inverse that's not a function. So here's the deal. Because y equals x squared is not 1-to-1, its inverse would not be a function. The true inverse of that would really be all of this, wouldn't it? And that's not a function. So, you are going to be asked questions like, does this graph have an inverse? And what it means is the inverse, does it have an inverse that is a function? You're going to say, heck no. Okay? The only way we can make this have an inverse that's also a function is to do what we call restrict the domain. And what that means is, I would say, as long as x is greater than or equal to 0, that thing does have an inverse that's a function. Because it would be this top half up here like like you guys were saying to me. I hope that as we go through this course, you find little nuggets of, oh, that's why I was told. Okay. Good. I'm on my way. Okay, so we're going to wait and see who walks in here. Okay. So what property of a function must exist in order for the inverse of the function to exist? The function must be 1-to-1. Please look at the bottom of your notes there. It says if f of x is not 1-to-1, then there are going to be repeated y values. When the inverse is formed, I'm on the bottom of the front page. When the inverse is formed, those repeated y values become repeated x values because the x's and y's switch. So the f inverse exists if and only if f of x is a 1-to-1 function. This piece right here, we're going to read through it. Please write it down later because there's a lot of writing here. Let's read right up here. If it can be determined that a function is 1-to-1, then the inverse of the function can be found. Fill in the following field, which will describe how to find the inverse of a function if it is established to be 1-to-1. Let's look at the numerical. It says to create a table in which the domain of f of x becomes the range of f inverse. So that means just switch the x's and y's. Go to the graphical. Again, make a table of points from the graph of f, switch the x and y values, and graph the new points for f inverse. Analytical, this is what you did in Algebra 2. You switched x and y in the equation because the domain and range switch. Because you're reflecting over the line y equals x, which means if xy is on the curve, yx is on the curve. Go to the examples. Okay. The first thing we're going to do is we're going to determine if the inverse exists, and we're going to justify it. If it does, find the inverse. If the relationship is in numerical form, give the table of values that would represent f inverse. These are in tables. So let's just look. Look at A. Now we're going to assume that those are discrete, that we would not be connecting the points, okay? does that function have an inverse? Meaning, is that function 1 to 1? So does every x have one y and every y have one x? Where's the problem then if you say no? Yeah, the y value of 2 appears more than once. So this will not have an inverse. So do you see the author's answer under A? F of x is not 1 to 1 because there's a repeating y value. So since f of x is not 1 to 1, f inverse does not exist. Do you see how the author's writing that answer? Okay. Go to B. Is this function 1 to 1? Not only every x has one y value, but does every y have one x value? Do you have anything that repeats? No, nothing that repeats. So look at how the author wrote it. F of x is 1 to 1 because the function, you don't have to say is discrete. You can say has no repeating y values. Now look at the table that the author made to show the inverse. Look what he did. He wrote x, f inverse of x, and made his table. What's going to be the first point in my new table, in my inverse? 6, negative 1. Yeah. Questions? Okay. Is this where we are? We good? Look at C. Does this graph have an inverse? Yes, because? Oh, good. The function's always decreasing, right? Yeah. So does the function pass the horizontal line test? Yes. So this function passes a horizontal line test, so it's 1 to 1. Therefore, f inverse exists. Now look at what the author did. The author wrote f of x is 1 to 1 because the graph passes the horizontal line test. Now, so what you're going to do, you're going to do what the author said to do in that big list up here. What we're going to do is we're going to write, let's do it like this, f of x and f inverse of x. Let's write a list of the points that are on f of x. So what have we got? Negative 5, 5, negative 2, 1, 2, negative 1, and 4, negative 4. What points would be on your inverse? 5, negative 5, 1, negative 2, oh, whoops, negative 1, 2. You plot those, connect them, and there's your inverse, which you can see on the author's picture, right? Okay, help me out. Please don't sit and try to write all this down because we got to move on. Look at D. Is this graph 1 to 1? Why? Right. So you're going to say f inverse of x does not exist because, oh, sorry, G. G inverse does not exist because G of x does not pass the horizontal line test, or you can say fails the horizontal line test. Mm-hmm.
Does it fail because it's going through point?
Fails the horizontal line test because you've got one y value, which is 1, that has 3 different x values. And see, if I reflected that over the line y equal x, I would have 3 x values that had the same y value, which would make that not be a function. You're welcome. Look at E. Does E have an inverse? Yes, because always increasing, right? So it passes the horizontal line test. So since h of x passes the horizontal line test, it's 1 to 1, so its inverse exists. You good there? Now, we're going to graph the inverse. Let's see if we can do this in our head. What are the coordinates of this point right here? So what point's on the inverse? 5, negative 1. What point is this? Negative 3, 3. So what point is on the inverse? You got the idea? Negative 4, 1/2. So what 1/2 negative 4? Negative 5, negative 3. So negative 3, negative 5. And there is your inverse. Is it safe for me to assume, and you're going to have to answer this, is it safe for me to assume that you remember how to do the process of finding the inverse? Where are you going, dude? What did you get a comp? Can you do the swap x and y and solve for y? Okay, because I know you beat that to death in Algebra 2, didn't you? That 2 years. Oh yeah, you did the yeah. But this one, let's look at this one. What does f of x look like? It's x squared that has had what done to it? You right 3 down 2. So it is a parabola that opens up. Right 3 down 2. Is that thing 1 to 1? No, because it fails the horizontal line test. A parabola fails the horizontal line test. So that function is not 1 to 1, so it does not have an inverse. What about letter G? What does that picture look like? It is a line. Now, okay, so we have to be careful though. Will a horizontal line pass the horizontal line test? No. Is that line horizontal?
No.
How do you know that? Well, this has a slope too. It's 0. It's a non-zero slope, right? Yeah. So it's a slanted line. Will a slanted line pass the horizontal line test?
Yes.
Bet your boots it will. So does its inverse exist? You bet. What about H?
Yes.
What's it look like? Yeah, you sound like a cat. Looks like that. What does the 2 do to it?
It's
Vertical stretch by a factor of 2. What's the plus 3 do to it? Left 3 and up 4. So the general shape is this. Is this 1 to 1? Yes. This is 1 to 1. So will it have an inverse? Yes. You know how to write inverse. You know it's like that, right? Okay. I'm not going to talk about it at this point. Yeah, I got to. Dang it. Let's do this one. Let's do this one. I didn't want to, but I think we need to. How much? Oh, we just got one more page? Okay, we'll be fine. We'll be fine. I was worried about time. So let's find the inverse. So this is, if you know how to do it, get after it. I'm just going to talk through it, and if you want to listen, fine. If you don't, that's fine too. I'm going to switch x and y because the domain and the range swap. And I'm going to solve for y. So I'm going to subtract 4. I'm going to divide by 2. I'm going to have to square both sides. Now let's think about this. I'm going to have to play with this here at some point, but I'm not going to play with it yet. I am going to write it like this. This is x minus 4 quantity squared divided by 2 squared, which is 4, equals y plus 3. So y equals x minus 4 quantity squared divided by 4 minus 3. This was g, wasn't it? G inverse of x equals something I want to look at real quick. Oh yeah. Are you okay here? Do you know what that looks like? What's that, Wayne? I don't know what your finger's doing. Yeah, look. What if I wrote it like this? Take a look. When you're dividing by 4, is that the same as multiplying by a fourth? Do you know what this looks like? This is a parabola that has had what done to it? What's the 1/4 do? We don't call it a squash. I don't think Miss Seegert would approve of the word squash. Vertical compression or shrink by a factor of a fourth. What else? Right 4 and down 3. Bottom line is this is a parabola. Right? Wait a minute. Wait a minute. We got a problem here. Houston, we have a problem. This original function here, wherever it was, what you said left 3 up 4? Isn't that right? Wasn't that right? Left 3 up 4? Left 3 up 4. Went like this. How can we have a parabola being the inverse of that? Yes. Yes. Now, I want you to look at this. This point right here is the point -3, 4, right? This tells me to do what? Right 4, down 3, correct? Now, does that make sense? The x's and y's swapped? But I cannot have a parabola. There is no way in this world that that is the inverse of that. It can only be half of it. Which half? The right half or the left half?
The right half.
It's the right half because you are reflecting over the line y equals x. But how do you indicate in this, how in the world do you indicate that you have a domain restriction? That's where you do the piecewise like constraint. You put comma, x is what? Equal to or greater than? No, here. 4. Yes. Yes. That's a little sneaky. Little sneaky. Then we just have one more page? All right. We got 15 minutes. Find G inverse. Go. There's the inverse. Now, if you had pre-AP Algebra 2, you hated this. Let's just do one of them. Let's find G of G inverse of X. Now, now, how do you do that? You just do what? Yes. What's going to go into G? G inverse. So what's going to go into G is G inverse. And where is G inverse going to go? All right, so this is going to be 3 times 2x plus 4 divided by 3 minus 4 all divided by 2. I put G inverse wherever I saw G, wherever I saw X. This is G of G inverse of X. What's nice about this, though, is that a lot of good stuff happens. Yeah, so where? So now my numerator says 2x plus 4 minus 4. So 4 minus 4 is 0. And now I've got 2x divided by 2. You remember? You remember that? When you do a composition of a function and its inverse, if a function and its inverse undo each other, you ought to be left with x. Uh-huh. So this one better be what? Better be x. If two functions are inverses of each other, there are two special compositions that will equal the same thing. Now notice right here, our functions are f of x and g of x. If they are inverses, if I do f of g of x, what better I get? I better get x. If I do g of f of x, I better get what? I better get x. Let's pick one of these examples. It says, determine if each of the pairs of functions below are inverses of each other or not, and show your work. Thankfully, the author gave you some pretty easy equations to work with. You want to do pair A or pair B? Okay, Coy says let's do A. And this is what you hated in Algebra 2. Especially pre-AP Algebra 2, because I think you had to do more of them. You have to do f of g of x, and you have to do g of f of x. And when you do each one of them, they have to equal x. If you compose both ways, you got to go both ways, and you get x, what did we just prove about f of x and g of x? They are inverses. So you will say f of x and g of x are inverses. If you get anything besides x, those functions are not inverses. Okay? I think that's all of this. If you have questions, I know we went through it fast and I told you to look at the author's notes so that we didn't have to write down everything. If you feel like we went through things too fast, we can talk about them. Tuesday is your quiz, right? So we'll take the first 20 minutes to study. So any questions you have, and then you'll take your quiz.